Well, thank you. I want to thank our hosts, Rackspace and Zipfian Academy, for doing the large amount of work it takes to organize one of these things. And what Nina and I would like to do is talk to you a bit about the topic of practical data science. Obviously not a term we own, but what is it? And how does it differ from machine learning or statistics? And does this work? Oh, that's awesome. So just a quick outline of what you'll get from this talk. Who we are, because we're egotists, so we know that. Actually, that was the great one, that the quickest way to find a narcissist turns out to be to ask them. That outperforms a number of psychological tests, was a recent result. Then we'll move on to a quick introduction to data science and a bit about our book, which Nina will talk about since she's first author, Practical Data Science with R. Who are we? We are, as Katie so generously pointed out, a small San Francisco methodological consulting shop. So we tend to specialize in machine learning problems. We're not really domain specific, but we've worked with banks. We've worked with well, a lot of banks, a lot of online retail, scientific work further back. But we basically, people have maybe painted themselves into a data science corner or want some training or want to start a new project, and we help them out. And we'd love to do that for you. We tend to work with other analysts and data scientists. We consider ourselves enablers. Can everyone hear me? Or, I'm good at shouting. OK. And then what we do when we don't have an editor is we write the WinVector blog, which is a bunch of insane rants about different algorithms related to machine learning. However, the book had an editor, so it was more specialized in readability for data science. So what is data science? It's something that's pretty high in its hype cycle. I mean, there's been a lot of jokes about it, which I think are quite good. Like, you know, data scientist is a statistician that works in San Francisco. Not my joke, but an awesome joke. And also, the other one is, why do we need data science? We've had statistics for hundreds of years. And by the way, we are releasing all these slides with crude speaker notes, so we'll be able to share that out. So you can take as few notes as you want. We actually have defined data science, and I wish we had this definition when we started the book. It's related to the book, though. The goal of a data science is to deploy a predictive model into production. So that means it's not just writing an analyst report. It's not just solving a problem, or it's basically writing a bit of software or a model that will survive in production unattended. It's also the absolute easiest goal from a statistician's point of view. And this is why data scientists sort of run where statisticians fear to tread. They're working on an easier problem, that what used to be called predictive analytics. And sort of in the stat hierarchy, the prediction's the easiest problem. Questions like, this person is expensive to insure, or this person from this population will be expensive to insure. Explanation is the next hardest problem. This person is going to die because of their extreme sodium intake. See, now you've got causation, which is now different than correlation. Things have become harder than mere prediction. And then the next one is prescription. If this person were to cut down their sodium intake, they may live longer. That requires even more methodology. It could be that the damage is already done. They've eaten enough salt, they're going to die no matter how they change their diet. The next part is, and we think data science is related to software engineering more than statistics is there's a client, and this is an idea we steal from agile development, that there's a client, either real or imagined, that wants this product in. So you answer questions relative to that client. Like, it's not, is this the best science? It's like, is this best for the business? Are we answering a question that's important to the business? Have we hit an accuracy level that's good enough? Is this data going to support a business? And the last bit, and a lot of people are writing on this, is repeatability in data science comes from scriptability and automation, which is, again, how it differs from an analyst behavior. Because we've seen a lot of analysts, they do a great analysis, and they're eaten alive by supporting that spreadsheet forevermore. We always say, at best, you're always on your penultimate run. So the data's going to change, some spec's going to change, you're going to need to rerun. So you need to basically be a bit of a programmer. And I think I saw a couple hands. I'd love to be interrupted. I'll go on. And that's our definition of data science. Okay, are we the only ones that feel this way? No. Cleveland himself proposed an action plan in 2001 where he wanted to expand the statistics curriculum into something he called data science. And he's already a statistician, or no, he's Is he a physical scientist? No.
He's a physical scientist.
He's a physical scientist, so maybe that's why he was bad to statisticians. But he thought that basically the classic statistics training didn't encompass enough software, enough hardware, enough data centers, that there was these concerns, cross-cutting concerns that needed to be added to the curriculum. And it had a couple other genesises. To our mind, data science is a process, which is, so it's not a Kaggle competition. We're not talking about taking one set of data once and tuning a series of machine learning algorithms. It's a bunch of stuff that not everybody likes. So if you don't like it, you may not want to be a data scientist. But it's basically, I've defined it as the process of deploying data-driven models into production. So the sub-steps that are most useful to the client are framing the problem, managing the data, deploying models. And building models is in there. To a lot of people, building models is the entire thing. And that's not the case. What you need to do is you often need large data sets, not always big data sets. So, because you're not doing econometrics. You're trying to find just correlations in your data. Cause is not a primary concern in these analyses. It's basically you're usually working in a business environment where they say, if this exact same customer that appeared Monday were to reappear Tuesday, should I offer them the discount or not? And so you're basically getting prediction by exchangeability or repeatability. It's basically, can you make decisions under repeated events, which is easier. And that's why often correlation is sufficient. And there's, like I said, there's some theory behind that. A statistician would say that's true if you have exchangeability. And then they would go on to say you never have exchangeability, so it's never true. Data science is a social event, which is another place that not all mathematicians shine. But the data scientist must competently interact with, and this is actually key in our book, managers, business owners, project managers, analysts. And the point is to competently interact with these people, you need to sound not stupid. So, and you need to be smarter than one of them in at least one of these areas. You also need to be willing to delegate, which means perhaps the machine learning expert is not you. It might be somebody working for or with you. You will have to work with statisticians. They've basically solved most of the hairy data problems you're going to run into. Statisticians basically understand how data goes wrong, how it tries to mislead you. And we've also noticed sort of an econometric feel to a lot of data science, where basically the model is not learned, which you do in statistics. You get the model from the mountain, and you're just trying to infer a few parameters. Like you think you understand how inflation's driven. You just need to know like a little bit of elasticity or something. And so they have a different way of fitting. Continuing on that, data science is multidisciplinary. Where does it come from? Well, the theoretical basis is statistics. Machine learning, as it came out of computer science, which differs from statistics. Typical machine learning, older machine learning algorithms were the perceptron, the neural net. Those basically, if you look at them, they historically didn't have a statistical basis. They worked because they failed to misclassify future data. They basically didn't meet a lot of statistical criteria. And then operations research, they solved a ton of problems of planning under uncertainty that you'll get into. The practical basis is computer and software engineering. What we now call data science evolved at places like LinkedIn, Google, Facebook. We've seen it come out of engineering groups, not labs. So it definitely has flavored it. It's a huge field. And what we've tried to done is, for this talk, we're going to get to something concrete. I've been making a lot of hot air here. So what I want to talk about is how to some techniques to effectively scope and organize projects, how to be an effective consumer, which means maybe a cynical consumer of machine learning results, how to choose among important model performance criteria. That third one is actually my favorite. You're going to be working with managers, which means you need to be sympathetic in your conversations with them. Most of them have no notion of classifier performance other than accuracy. That's what they know. So you need to basically be able to educate them away from accuracy into other criteria, a couple of which will be the only concrete thing I talk about, some cool criteria. And then the last one is produce effective data visualizations. That's kind of a lie in the presentation. What I'm kind of saying is I'm going to sneak in some graphs, and I've automated making them. And so what it is you spend as a data scientist, maybe the hour to build a graph that an Excel analyst could build in 15 minutes. But you impound it as repeatable code so that you have that graph available while you're doing your exploratory data analysis, or your EDA. So you make many, many more copies of that graph. So your amortized cost, the first one costs an hour when it should have cost 15 minutes. The next one costs 30 seconds because ggplot2 is slow. And then eventually, and we actually are huge ggplot2 fans. And so that's basically what to get from the next bits of this talk, which will be more concrete. Just one aside, why I'm stealing a bit of Nina's presentation here. Why is the book in R? We wanted a minimal environment where you could do everything. So we're not saying that R is better than Python. I mean, frankly, Python's the better programming language. But we feel that R data frames are a little quicker than pandas, that basically R is a quicker, more integrated environment to try to bring somebody new into. And if I've offended anyone. So our example problem, a project goal, basically build an Obamacare system that you want, or an aid to Obamacare, that you want to build a phone outreach system where you're going to call people that maybe don't have insurance and offer them assistance to sign up. And let's not just make this a value judgment where that's a good or bad thing. It's just your goal. It's what you've been told to do by the business person. The client asks, and this is the most important part of the data science project. And we're emphasizing it because we feel there's an urge for people to skip over it. I was trained as a mathematician. So in my world, the project manager has done a great job making a very specific problem that only I'm smart enough to solve. That's never how it works in business. They have an ask that's kind of vague. And to the extent that it's specific, it's wrong. That, that you're not the genie in the bottle that you said to predict who didn't have health insurance, and I said nobody does, so I win. That you need to basically, it's a cooperative thing. So what the client's initial ask is a score that estimates the probability that a person has insurance based on a few census facts: age, income, occupation, and location. And the reason we're using census is that data is available. Maybe that's important. That, let's use measurable facts. We've talked them out of a predictor that says whether they have insurance or not to a probability score. That we could do a prediction, but you want a score. And the idea is by talking them into that, they can then recalibrate their business without our aid. Like if we say this person has a 70% chance of having insurance, they go, we probably don't want to call them. If their cost benefits analysis between bad calls to people that have insurance, which are wasted calls, and missing people that don't have insurance, which are lost opportunities, if that benefit analysis changes, they can say, hey, I now have enough staff to call the people at 70%. And if they don't have enough staff, they can say, I'm going to call only people that have a 30% chance of having insurance. So basically, by giving them a score, we maybe haven't taken over and held their entire business practice hostage to our machine learning algorithm that just says call, do not call. So they maybe originally asked, I need to know whether to call somebody or not. And instead we say, what you really want is the probability they have health insurance. Then your policy people can reset your business at a later date. So first point, how to set the effective scope. We suggest actually delaying any math or analysis. That basically do some cooperative initial scoping exercises. A lot of these exercises are designed to kill the project early or front load risk. Basically, the secret to happiness is spending longer times on things that are going well and shorter times on things that are going poorly, which means kill things that are going poorly. So we've run into this with our clients. Estimate what fraction of your targets can even be contacted. So they were saying they were going to interact with people that may not have health insurance to offer them health insurance. We've found often that the people that contract us in don't have the authority to act on. But you'll find out that there might be some federal regulation that says they can't dial the phone. So you build this great model, then they found out, oh, we're not allowed to call anyone. This actually happened to us at a bank that was going to offer a product, and then they found out they didn't have the authority. Yes?
So if you're doing something like this, how would you know to ask these specific questions?
Well, so your question was, if you're doing this, how would you know to ask these specific questions? So you're coming in, you sort of do a dance. Why do you need data science? Oh, I have this business need. Okay. Do you have the business? Like one time we were brought in by a support group. That was a bad sign. We weren't brought in by the business unit of the bank. So really, do you normally offer products to people? Then why does it help you to know better? So it's basically sort of a little dance is the answer. Then, see, a lot of these exercises are along that flavor. Like, what if everyone has insurance, everyone doesn't have insurance? Then there's no modeling exercise. This is another one that we found out when we've gone into large companies. We've had small clients and big clients. Sometimes they're commissioning a prediction project that I want to predict whether this person wants this product. And they may actually already have the answer in their database. That the person may have filled out a survey saying they want to be called on this product. And actually my census one, the census actually has some columns as to whether the person's indicated they have health insurance or not. So this, in reality, should not be a prediction project. It should just be an engineering project saying, actually, the data set you claim you have has the answer. And often, if they don't have a data dictionary, they don't know this. So you're not trying to sell prediction. You're trying to stay very sympathetic to the business goal. And if they can succeed without prediction, you want to do that. This one is another bit of a little dance. Estimate type 1 and type 2 error costs. Hate that phrasing. So type 1 and type 2 errors, it turns out it's on your point of view which is which, and I'm going to get it backwards, so I'm not going to use that term. But basically, when you're doing this calling people who may not have insurance, there's two types of errors you can make. You call them and they have insurance, or you don't call them and they don't have insurance. And those have different costs. So if you call somebody and they have insurance, it's wasted time on your call center, and maybe you make Fox News that the federal government's calling everybody to cancel their insurance. However, the cost of not calling somebody with insurance may be different. Like that might cause that family to incur a very great cost if they have a medical accident. So what you do with the client is you say, well, so your type 1 errors, your errors of calling people that don't need to be called, well, those are obviously in dollars. Like, how much does that cost you? And they're, oh, that cost me $50 in calling center volume. Every time I call somebody, that's $50 wasted if I call somebody with insurance. So then wouldn't it be great if the other sort of error was in dollars? What is it to you to miss an opportunity to give somebody insurance? Oh, it's $1,000. They'll never answer, because they'll be, how would I know that? But what you do is you start building initial models, showing them your error rates, and then you say, well, if it was $1,000 for everyone you miss, would this work with this error rate? And they go, no, it wouldn't. Maybe. And what they'll do is they'll sort of debate with the devil, like the 4 stages of grief. They go, maybe it's only $500 to miss somebody. Maybe I don't care about people that much. But you do these rounds, and what you're doing is you're sort of weaseling on what sort of type 1, type 2 error model, precision recall, sensitivity, specificity model you can make. And you're not in your final model. You might be able to improve. And they're sort of weaseling on what the two costs are. And you're sort of doing this meet in the middle thing. Like, can you make a perfect model? Okay, because then I'll make my error costs infinite. No, I can't. Okay, well, $1,000. Okay, I can do better than that. $2,000. And so that's kind of the fun thing. What should a person expect from a machine learning result? Well, so we talked this client into the score, the probability of a person having insurance based on other census data. So we need to then educate them, and maybe ourselves, into metrics on which model is doing better. Suppose we have more than one data scientist, we have competing models. And the issue here is we need a broad vocabulary of scores. And the thing that we think is never taught is we need to pick a score that's sensitive to the business needs. And what I'm going to specifically go over some of these scores, just a small smattering in their actual things. And we're here to basically make fun of AUC, because that's called area under the curve. And it is a very interesting and very high quality overall model quality measure for a score. But the thing I'm going to say is it's not tied to any business need. Your client is never going to make an extra dollar for every point of AUC. So what we're trying to do is find a metric that leads up to some business need. However, as talking among modelers, you may use AUC to bake off your early scores before you get the client needs. Where basically you don't know what precision and recall, you don't know what costs you have, what precision recalls are preferred. AUC is interesting. But we're going to go through some rank lift metrics, Deviance type metrics, which are actually a personal favorite of mine, even though they don't always link up to business, and then some AUC. But the idea is you need a broad vocabulary of scores you're very comfortable with, in that you feel you can use them, you understand them, and you can teach them, which is why I'm kind of going to go through them here. Either you already know them and you can see maybe how I try to teach them, or you don't know them and maybe you can pick up how I'm going to teach these 3 scores. This is the first thing we do as analysts. And I did promise this would get more specific. So what we do here is we call this the double density plot. And it is a non-standard plot. Not everybody likes it. Not everybody does it. But I learned it from a physicist. But and I also call this running Bayes' law in your head. But what it is the red curve. Let's do the blue curve first. Let's be positive. The blue curve is the distribution of classifier score. So the x-axis is what score the classifier gave. And the blue curve is how that score is distributed for people in our training set known to have insurance. And the blue curve looks good. It's mostly peaked at 0.8 and above. And so it says basically the model for people that has insurance tends to predict they have insurance, which is awesome sauce. Until we look at the red curve, which is also peaked at around 0.8, not quite as sharply as the blue curve. And yeah, both of them have some dispersion. Red, thankfully, has a little more. So the model, in general, says for people that don't have insurance that they probably have insurance, which is bad. The ultimate good version of this graph would be the red curve would be a spike over at the left, that for people that don't have insurance, it tends to say they do not. And you'd have separation of the two distributions. This is bad, but fairly realistic early on in a machine learning project. And what it's saying is, what the data said is most people have insurance, we found out. And a lot of the features that were available in the census data set don't predict it very well. In this model, we built off a very tiny number of variables. I think just age, declared occupation, and state. That we deliberately built a dumb model. So most of whether somebody has insurance or not doesn't depend on the variables. However, the reason I call this Bayes' law in your head, if the model could separate people that had insurance and don't have insurance, then reverse it. The having insurance and don't have insurance should basically separate the model scores. Basically, a long-winded way of saying the has insurance group should be a spike at the right, and the does not should be a spike at the left. These graphs are my absolute favorite for early model exploratory. Things you can see in these graphs, to look out for in these graphs, are a degree of dispersion, spikes, overlapping distributions. These two distributions are not very different. And also it's a density plot. So both these areas are scaled to 1. And this smoothness should be suspect. That's probably from the kernel smoother that drew the graph. Probably not a feature of the data. So when it's that. And the other thing to look out is for multiple spikes, because that's usually subpopulations that are behaving differently. That you'd kind of like these to look like 2 spikes separated and not have 3, 4 hair. I'm going to come off that. So this graph requires something I'm kind of against, analyst intervention. That you need to look at it to say whether it's a good model or a bad model. So let's move on to, again, a non-business motivated score, but a mechanical score. And again, these slides will all be out. This is a score that's a little more exotic. It's called the Deviance, and we'll actually work one together. And but what it is, it's basically, on average, how log dumb is your score. So if somebody has insurance, and it says it's near probability 0 they have insurance, it makes this heinous error. You go, well, that's going to cost you. You know what you're going to get with your probability 0? You're going to get log 0. You're going to get minus infinity points for that. Similarly, if they don't have insurance, we give them the logarithm of 1 minus their score. So if somebody doesn't have insurance, and the model runs in all excited, and we're going to work this example more concretely, it says this person positively has insurance. And you go, well, you know what? You get your log 1 minus 1 for that. Another minus infinity. The mathematical definition, and this is sometimes where I get in a little trouble with statisticians, is the deviance is actually minus 2 times the log likelihood of the data, subtracting off a shift factor from the so-called saturated model, which is almost always assumed to be 0, even when it's not. Though if you forget to write the S, even though you're going to substitute in a 0, you get yelled at by statisticians. The cool thing about the deviance, and Nina has an article about this on our blog, which we'll point out to later, is the deviance. Again, we're going to work the deviance for you in a couple of slides, so just take this on faith. The deviance is basically the log stupidity of your model. You can also compute the log stupidity of using the grand average. So if 70% of the people have insurance, your only prediction score is 0.7. 0.7, 0.7, 0.7, 0.7. That also has a deviance. That's what we're going to call the null deviance. That's the deviance of a null model, the best guess at the grand average. The deviance, So a perfect model has deviance 0, and a bad model has very large deviance. So the deviance divided by the null deviance, so it's basically subtracted from 1, looks just like an r squared. And in fact, it is canonically called a pseudo r squared. It is basically what fraction of the variation you're explaining. So if your pseudo r squared is 1, because you took the deviance down to 0, you're explaining all the variation in people having insurance or not. Nobel Prize in cleverness. If your pseudo r squared is near 0, your model is no better than the grand average. And so, thanks for playing. No good. This, I believe, you can't do all the math to a client, but I think if they've taken a stat class, they may know about variance and saying, well, what fraction of the variation are you explaining? Deviance can be sold as that if you renormalize it this way. Actual deviance calculation. So we have 4 examples of people that had insurance. First 2 people had insurance, second 2 people did not. Model predicts, first prediction's great, that this person had a 90% chance to have insurance. Next prediction's less great. It said that this person had a 10% chance to have insurance. Third prediction's awful, again. It said that a person that did not have insurance, it said 90%. And fourth prediction's good. A person without prediction, it said low probability. The deviance calculation, I missed a parenthesis. The deviance calculation is they get a log 0.9 for the first one. Logarithm of 1 is 0, so they get a very little penalty. Awesome. They get a log of 0.1 for the next one. 0.1 is suspiciously close to 0. They get a penalty of minus 3.2. They get an ouchie. Third one, they get an ouch. Fourth one, they get very little penalty. And the neat thing about deviance is if you're using logistic regression, which is my personal favorite machine learning workhorse, it's optimizing deviance. That is what's wired into it. So that's another thing to check when you're scoring a model is, even though it may not be the customer's criteria, check the criteria that the model was optimized against to see if it's at least doing good in its own fantasy world. Back to evaluating classifier graphically. Basically, you don't have to be mathematically rigid on this. You should be able, from the double density plot, develop a ton of good metrics that might be important for your client. You just need to interview them. Like, what does a false positive cost you? What does a false negative cost you? And they're not going to be able to answer. But as you start showing them different model qualities, they might be able to develop an opinion. Why we recommended a score, and I alluded to it earlier, is when the client picks a threshold, say in this case 0.7, so it says I'm going to say everybody with a prediction score above 0.7 is somebody that may have insurance. I'm going to stop doing double negatives because I confuse even myself. Then what happens is the red curve is the people that did not have insurance from the double density plot, and I've split it into 2 graphs. So everybody on the top red plot that's to the right of the 0.7 line, the model says they have insurance and they did not. Those are all errors. The shaded region is all error. Similarly, on the bottom graph, those are all the people, distribution of scores, people that did have insurance. Everything below 0.7 which says does not, those are all errors. So this, you can perceive the area of the curve. You don't have to do calculus. You can just say, well, it does great on people that has insurance, gets very few of them wrong, and it does horrible on people that do not have insurance. From this graph, if you don't normalize it, gives you something. Again, we're going back to standard statistical notation, which I do actually like. This is called a contingency table. And it's also, when we scale it correctly, it's also called the confusion matrix. So what we've done is the rows, let's just look at the top table that has the counts. And I actually trained, so each count is a training datum, or a test datum, sorry, that I held out during training. The rows of the top table are the truth. The top row is they did not have insurance, bottom row is they did have insurance. The columns are labeled by the classifier prediction at the 0.7 threshold. So a good classifier would just be diagonal, that everything it says doesn't have insurance, and everything it says does have insurance, has insurance. This one, from this table, and you should basically always to your peers present the confusion matrix, because you should be doing your arithmetic. You should be noticing, oh, I'm adding up these 2 guys in this row, almost everybody in the world, all but like about 85 people have insurance in the training set. Very unbalanced. Oh, this model's good in the bottom row and horrid in the top row. You can start, and then you can also renormalize the table. You can divide by the totals, and you can get what fraction of your training population is in each region of the confusion matrix. And every stat you've heard of for classifier quality, sorry, no, it's false. Many of the stats you've heard of for classifier quality are simple functions of the confusion matrix. So let's just name a few. You've got accuracy. That's essentially what fraction of the mass is on the diagonal. You've got precision, you've got recall, you've got sensitivity, you've got specificity, you've got false positives, false negatives, true negatives, you've got, I think it's called drop. Each one of those is a properly rescaled bit of this table, either a cell or a cell divided by a row total, a cell divided by a column total, or a cell divided by the whole thing. So it's basically, you should always be looking at one of these, possibly normalized, to get your initial sense of this. And then there's further derived metrics like F1, which I don't want to get into, which are that. However, I said the double density plot, which I personally love, is not standard. What's the standard way of graphically dealing with this? And again, you would try to introduce some of these to a client in a longer period of time than here, not to really scare them. So the standard graph is the receiver operating characteristic plot. And I was really careful not to say receiver operating curve. Again, get that wrong and cluck, cluck. But this is the same graph as my double density plot. And what it is the statistician, well, actually engineers in this case, noticed that classifier threshold is an irrelevant variable. It's a nuisance variable. I don't care whether you're cutting your scores at 0.7 or 0.9. I want to know if to get 70% of the people that don't have insurance, how many of the people that have insurance do I have to pick up? And I probably got that wrong because there's specifically curves. But basically the idea is that classifiers are often most easily characterized as two-dimensional beasts. They sort of have this accuracy on the true set and this accuracy on the false set, and you want to trade those off. Like if you're a machine learning guy, you call those two things precision and recall. If you're a doctor, you use slightly two different unrelated, different statistics called sensitivity and specificity, which are different than precision and recall. But the idea is you always want two accuracy measures. And what this is saying, the ROC plot is take two of these accuracy measures, sweep the threshold, build from our score every possible classifier, and just plot what false positive rate and true positive rate it achieves. And so the true positive rate is of the things it said, I'm going to stop doing the double negative, of the things it said had insurance, what fraction did. No, sorry, of all the people in the world that had insurance, how many did it get? It's important whether you get the denominator right. Is it what you predicted or the entire world? And the false positive rate is which ones you missed. And again, getting the denominator right involves looking at my notes, which I'm distributing the slides with the speaker's notes. But each one of these dots is an actual achieved classifier. There's some threshold that achieves this one, this one. There's no threshold that achieves in there. Most people don't do the dots. And the thing is, your graphing software, the shaded region is called the area under the curve. And we can, again, being humans, we're good at perceiving area. And some fun facts are the diagonal line is a typical useless classifier, just randomly scrambling the data instead of sorting it. And I swear I've been at a KDD where somebody had a curve under the line and was yakking on about it. And so basically areas under the curve of half or less are useless to worse than useless scoring systems. An area of 1 would fill in the entire set, which means you have a perfect classifier. The way to read it is down here you have a very accurate classifier that's useless on one class. That it doesn't make any false phone calls, but it also doesn't call anyone. Because there's two perfect classifiers that if you were the genie in the bottle, you could get. So one is the one that says everybody has insurance. That has pure recall. Gets everyone, but it's very nasty. And the other one, you say nobody has insurance, and you just say, well, anyway. So you can get those are represented as two on the diagonal. But what you want is the classifier that gets them all right, and that's the top left corner. And if this curve had area 1, it would be up there. So how do you use these plots? These area under curve, I disrecommend it for clients, but I do recommend it for peers. So here's where the area under the curve, or ROC plot, really shines. This is my new improved classifier. I added a couple more variables, which is the usual way of improving a classifier versus monkeying with machine learning algorithms. And you can see it looks slightly different, like it's got dots everywhere. and it's better. You can't tell, right? 'Cause it is not that much better, and there's just no visual way to tell this classifier from this classifier, other than there's a few more dots. But the thing is, with ROC curves, you can stack them. So the red ROC curve plot is the original classifier. The teal one is the new one. And the idea is, almost everywhere, the teal curve is up left from the red curve. It dominates it. There's basically the client might pick different false positive rates and true positive rates as his business policy. That's the client's responsibility, though you have to educate them into it. But there's no point where the client will want the red classifier instead of the teal one, or very few points. And so basically, as a machine learning peer, you can say, look, I think my classifier is better than yours, that we should go with this methodology. And this is what the intuition behind area under the curve is, that area sort of predicts containment or domination, though there's some technical reasons not to depend on that. But that's the point, is the ROC plots can be stacked. So, and often in machine learning projects, you were talking about stacking subtle improvements in classifiers. We're not talking about moving from a CRUD classifier to the right answer. So you're not going to get this aha plot where the double density, looks kind of wishy-washy there, then all of a sudden separates to two spikes. Well, you should be so lucky. Moving evaluation forward. This is basically what we just went through, is something that I'm really passionate about, is basically working cooperatively with the client, which means trying to get them into our terminology, which means adapting it to them, that they don't need to go through the suffering I had to learn it. But sharing all the results, like here's a bad classifier, now you know what bad ones look like, here's a good one, and here's how we're doing. But basically, try to educate them into being able to pick one of sensitivity, specificity pair, precision recall pair, lift. Actually, most clients invent lift all by themselves. So what they do is they sort the data by the classifier score, and they say, my call center, so you put all the people that the model says probably don't have insurance at the top of the list. Sort it by the classifier score, and they go, I'm not going to pick a threshold, I'm just going to start calling down the list in order. And the lift is, in the first 1,000 people you call, how many didn't have insurance? Versus if you did it in random order, how many didn't have insurance? So maybe 30% didn't have insurance in your model, but in the random order, maybe 10% didn't have insurance. So you represent a lift of 3, that their call center is 3 times more effective using your model. And that's something we found you have to educate clients into. Is like, what's the value of a model that's usually wrong? Well, it's often wrong, but it's 3 times better than random. And often I'll find clients have invented a lift-like metric on their own, which is really cool. We don't recommend with clients using AUC or accuracy. Accuracy confuses type 1 and type 2 errors, which are rarely true for the business. Lost opportunities are different than sunk costs. And there is a Wikipedia article claiming AUC actually is dimensionally valid. And actually I have a proof on the web, on our blog, that that's false. And that's kind of where I'm going to transition out, is when we're not excitedly trying to explain very basic scores, which I think some of you already knew, or if you understand them now, you probably understood them before I started, because this is much more compressed than with a client. When we're not talking about that, we're writing crazy articles, both of us, which are either statistics for engineers or engineering for statisticians. And it's always a debate, which is more dangerous, a program written by a statistician or analysis performed by an engineer. However, so there's one called setting again, all these URLs, we're giving these slides out with crude speaker's notes. All these URLs are available. But one is setting expectations in data science projects. Fun little activities like writing the right answers on 3x5 cards. Seeing if building a worse classifier kills their business. If not, then probably building a better one won't help their business. Sort of a secant method of saying whether their business is sensitive to quality. Nina has a really cool series called Statistics to English Translation, which I think does a great job of both defining metrics and separating the issues of p-values from accuracy measures, and basically saying significances are different than accuracy scores, and not to use accuracy. Some stuff on A/B design testing. just a very angry rant about p-values that basically, this is something that a lot of us engineers miss, is we'll often report something like this, the quality of a classifier as if it's a single number, but really everything we've done is an experiment, and it could be that we just got lucky. In fact, we probably got lucky. We were probably tuning the classifier for every week, and the first 4 weeks our boss asks us, how's the classifier going? And you go, well, my dog died, I gotta go. And then the 5th week when it's working well, you go, awesome. And so what happened is that might be by chance. You may have been trying random machine learning ideas, and on the 5th week, it's not really a good one. It just happened to look good. It failed to fail, as we say. And the p-values is how a statistician says it very concisely. Statisticians are very good at being very concise, but you want to be a little longer there. It's really a theory of significances and what's the odds of seeing a result this good by chance. And that's my rant saying worry about correctness and repeatability, which is what significance is measured. Is this a real result or chimeric one, not what's my exact p-value. And then Nina had a really cool article. There's sort of a hipster convention that Bayesian statistics is a little cooler than frequentist. And what she's correctly pointed out is actually which one you need to use is determined entirely by the nature of the question you're asking. And so if you're asking a question about repeatability of experiments, it's a frequentist question. If you're asking questions about estimation of unknown parameters, it tends to be a more Bayesian question. And basically, being careful about what's really being asked picks the methodology for you, which means basically, and this is sort of like our point on R and Python, you don't have the luxury of knowing just one. You need to know both methodologies and use what's appropriate. Engineering for statisticians. Minimal version control lesson, use it. Basically, software engineers have solved a bunch of problems that involve risk and losing data a long time ago, and basically us as analysts need to do that. Some R styles tips. You don't need to understand pointers to program using R. We actually feel bad usually introducing people to new programming languages, and R has some features very much like MATLAB that make programming for beginners much easier because it basically avoids object aliasing. If you have a copy of a data frame and you alter a cell, somebody else's copy does not show that. And that's very expensive and very cool feature of R, but it meets people's naive expectations. This is on the negative side, an article by Nina that we discovered that 2 of the most common R models, LM and GLM, they get bored and copy like an entire set of your environment, your data frame, your dog. They hide all your data inside the model. So we've seen that it's just a bad engineering practice because so when you do a model fit, they hide all the data, and Nina figured out how to nuke it all out because LMs and GLMs are famous for being very small models. They don't need to save all the data like a nearest neighbor does, but it turns out just due to historic implementation considerations, R does this. I'm sure no other programming language does that. And that's kind of where we're going with that. And what I'd like to do is switch over to Nina. If I've sort of established that we're talking about data science as a practice, and I think that maybe, we did some math, but it's really about the practice. We'd like to just say how the book dovetails into that philosophy.